Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation FETs, physics perspective. So, this is lecture number 11 and the topic of this lecture is capacitance modeling for high and low frequency. So this is basically class 3 of week 2. So, let me give you an outline of what is expected from this class. We will be first of all explaining to you the low frequency terms, especially the small signal model, and that too limited to the intrinsic part. I will explain each one of the term individually to all of you. We will define the small signal equivalent circuit. Then we will look into the small signal model for drain to source current, which is IDS, and then small signal model for both gate and body current at all the three regions of operations, which is strong inversion, weak inversion and moderate inversion. And then we will have a generalized model for the transistors at low frequency. Once we finish with low frequency, which is typically of the order of few hertz, right from say 6 to 7 hertz to about 100 hertz is typically considered to be low frequency small signal model for intrinsic part, and then we will go to medium frequency small signal model for the intrinsic part, where we will be looking into only the intrinsic capacitances and not extrinsic capacitances in general, and then we will recapitulate what we have learned within this lecture. So, with this initial sort of prelude to the whole thing, let me start with the first of all the small signal equivalent circuit, right. Let me first of all explain to you the last part, the last point which you see here, which is basically the intrinsic part of a semiconductor. So, let me give you a brief idea about what an intrinsic part of a semiconductor is, and then we can concentrate on the first 2 points of the equivalent circuit. So, if you remember your previous lectures, we have this source and we have this drain, we have this oxide layer and then metal layer here. This is your gate, right, and then obviously the substrate is here, or the body is, or let me put it body because there. Then we define the intrinsic region to be this much. This is defined as my intrinsic part, right. This is intrinsic, where you have actually the current flow, and anything outside this is basically my extrinsic part. So, the intrinsic part takes care of the active area of the device, where actually the current actually is flowing, though the current is also flowing in the source and drain region, but the origin of the current is primarily in this region near the silicon dioxide interface. So, we are trying to emulate basically a current source through this intrinsic part, which can be actually done using this gate bias, and we know that when Vg is obviously greater than threshold voltage of the device, there will be a thin inversion layer here which will result in the current flow. Now, we define this to be the intrinsic part, and the other part is basically your extrinsic part, right. Now, let me tell you what the intrinsic part, how does it differ from the extrinsic part. The extrinsic part will contain all the resistances and capacitances of the contact. So, you have this gate contact, metal contact, you have the source and drain metal contact, you have this bulk metal contact. All the resistance of these contacts and the capacitance modeling will be extrinsic. All internal, which is intrinsic, will consist of resistive and capacitive modeling of the intrinsic part, right. However, since this intrinsic part is responsible for the current flow, we will also look into the fact that how does this part, specifically the structural parameters of this part, influence the flow of the current. And that is the reason my last point is there, that we will be actually looking into the intrinsic part of the device. Now, how do you define small signal equivalent circuit? Now, you see, we have already defined to you that there are 4 terminals in a MOS device. Now, let us suppose I give I ground source and bulk, but I give a potential on the gate side and the drain side. However, I ensure that that the variation in the terminal potential on the gate and drain are so small that the resulting current equations, right, can have a linear relationship with the voltages available between gate and drain, then we define that to be as a small signal, right. Typically in local sort of in generic terms, we define small signal as if the input voltage which you are putting on the gate side is shifting the bias point of the device by plus minus 10%. So, if the bias point, if the bias points shifts by plus minus 10%, then you would expect to see what is known as a small signal. This is a much more quantitative definition, but if you want to look at a very qualitative definition, the first definition works fine, that if the terminal voltage variations are sufficiently small, right, so that the resulting current which you are seeing, the resulting current variations which you are seeing, del ID, and can be expressed in terms of the change in the terminal voltage in a linear expression, then we define that to be as a small signal equivalent circuit, which primarily means that that the current is as I discussed with you, linear function of the variations, and when you increase the terminal voltage, let us look it from the other side, when you increase the terminal voltage swings, variations, if the current becomes a nonlinear function of the applied gate, change in the current becomes a nonlinear function of the applied gate biases, then we define that to be as a not a small signal equivalent circuit. What we will do in the subsequent chapters is we will try to figure out these linear relationships, and we will try to develop a linear circuit. These circuits are known as small signal equivalent circuits. Why it is important that they should be linear? It makes my life easier in terms of the mathematics of the device, right, and still without sacrificing the content, the basic content of the device, we are still able to give you the idea of the device itself, right. Now, what we do in general in most of the general cases, this is IDS actually, this is drain to source to drain current, you can actually neglect this part, drain to source current, which is IDS, right. So, what we will at low frequency, when we do, or the frequency is very small, when this frequency is small and it is a small signal, I mean to say the frequency is the order of few hertz, and and so the frequency is of the order of few hertz, and your signals del of V is of the order of few 10% of the bias points. If you maintain these two conditions, we come to this low frequency small signal model. Now, in most of the cases, we will assume that the only current flowing in the device is basically drain to source current, right. However, when you go for very advanced process nodes where your oxide layers are very thin, then you will also you will be having a gate current, you will have also a gate current, right. Why gate current? Because if the oxide layer is very thin, and if you apply in the metal side gate voltage, then there is electric field which is occurring in these dimensions. If it is a positive gate voltage, then electrons can actually punch through, sort of a tunnel through this oxide layer and reach the output world, and therefore there will be an IG or the gate current. So, in general, you can have a gate current also being generated, right, when your oxide layers are very thin, right, and this happens with low technology nodes. The second problem which we encounter is that if you have your if your drain voltages are relatively very high, right, of the very large value, then if you can understand, there will be heavy electric fields near the drain end. Why? Because you are reverse biasing the drain to the body. So, the electric field will be very large, right. When the electric field is very large, it is almost like a reverse junction PN junction diode, because of which there will be impact ionization. What is impact ionization? Impact ionization is something like this: an electron is travelling from this part to this part because of high electric field. As it strikes one of the lattice atoms, because of high energy, let us suppose it generates one extra electron here, right, and then electron, this also travels very fast because of the high electric field, right, and then this also generates one extra electron, right, and so on and so forth. So, what will happen is that you will get a bunch of electrons right, or a bunch of holes will be generated which will be very energetically high, and this might cause a body current. So, there might be a current which is flowing through the body. So, if you apply a positive bias on the body side, all these charge carriers will be taken care of in the body, and there will be a body current. But in most places the body is generally grounded. So, then also we say that my del IB will be approximately equals to 0. So, the change in the current will be approximately equals to 0. So, we assume in the first place that Ig equals to 0, and we also assume that IB equals to 0, but at low technology nodes this assumption does not hold good, correct. Let us come to now the small signal model for drain to source, right. We will again assume, as I told you, that IB and Ig are both equals to 0. You see the second part, IB and Ig are both equals to 0, and we are trying to evaluate the small signal model for the drain to source current. So, we will try to find out how drain to source current varies with respect to these signals. Now, of course, the drain to source current IDS is basically a function of gate voltage, bulk voltage and drain voltage. Now, I will explain to you what do I mean by that. This we will encounter later on as well. So, if I have a MOSFET which is available here, right, if I have a MOSFET here, then I told you earlier also that I generally my source is grounded, I apply a drain bias, right, I apply a gate bias, and my body is also grounded. So, body and gate are grounded, whereas gate and drain are given some potential. However, whenever we write Vg, we do not write Vg, we write Vgs or Vds or Vbs, right. What does it mean? It means that the voltage at gate, drain and bulk with respect to source. This is my source. This is known as a sourced referenced modeling. This is referred to as a source referenced modeling. We also come to the second part, and this is where a new thing will be added here. You see the body, you can also have a body referenced modeling. Then body reference modeling will give you what? VGB, VDB and VSB. With respect to body, you will have the source voltage, with respect to body you will have drain voltage, with respect to body you will have gate voltage. So, what is VGB? VGB can be written as VG minus VB. Now, since both are grounded, obviously VGB will be equals to 0 in this case. No, sorry, since gate is giving a positive voltage, it will be nothing but Vg because Vb equals to 0. However, if you take VDB, VDB will be again equals to Vd, and VSB will be equals to 0 because both source and drain are bulk are grounded. So, this is known as a body referenced modeling. This is referred to as a body reference modeling. So, we have two types of modeling available to me. One is a source reference modeling, where you take every terminal except source with respect to source, and we have body reference where every terminal is taken with respect to body, correct. So, these are the two types of sort of referencing we have done. We will see why it is important in later courses. Let us come to the first definition, which we have already done, but let me give you a framework for that. And the first small signal model, or the first small signal parameter which we are going to see, is basically known as gate transconductance. This is known as gate transconductance, GM. What is GM? GM is basically del ID del VGS. Again, you see very clearly this only depends upon, if you look very carefully, this del ID del VGS tells me that any variation here del VGS will result in the change here. So, we are talking about the intrinsic region only. So, we are just concentrating on the intrinsic region, assuming that your VBS, bulk to source and drain to source, are all 0, right, or they are held constant, actually not 0, they are held constant, right, because if you put 0 there will be there can be never be an del IDS. Why it is held to 0 is because this gives me an idea that the change which is happening in the drain current, right, because of the change in the gate voltage, primarily is just because of the gate voltage. No other voltage is responsible for the change, And why is it so? Because if you make the wage, and why generally why do you require my GM to be relatively high? The reason is, when you want GM to be high or you make GM high, then what you do end up is that you make it more sensitive to variations in the gate voltage. So, the transconductance should be high, and the reason is, if the transconductance is high, primarily means that for the same change in the gate voltage, if your change in the drain current is relatively high, it means that you have a large transconductance, which means that the device is relatively more sensitive to the variations in the gate voltage. Are you getting my point? And that is the reason GM should be as high as possible. Let us look at the second transconductance, and this is known as GMB, that is the gate substrate transconductance, which means that if I vary my VBS, that is why I have told you in my previous discussion also, that if I vary VBS, I would also see a change in the value of IDS. Why? Because let us suppose this is p-type substrate, you make it positive in nature, you make it positive, then you are pushing the holes inside, right, and therefore you require a larger gate voltage to switch on the current. So, your threshold voltage increases. When threshold voltage increases, your current actually changes, right. So, therefore, with varying values of VBS, right, you will actually see a indirect change in the drain current, and this is referred to as GMB. Ideally, I want my GMB to be as small as possible and my GM to be as large as possible, because I do not want a substrate to interfere with the overall current. And if there is some leakage happening in the substrate, if there is some problem with the substrate, if it affects my overall drain current, I will be in a big problem, and that is the reason I want it to be as low as possible. Let us come to the third one, which is known as GSD or GDS, as we refer to it, and that is drain current with respect to a change in the drain to source voltage. So, del IDS, del VDS with VGS and VBS keeping constant, which means that the gate to source voltage is kept constant, which is well above saturation. So, this is actually in saturation, we can say, which is in saturation, and my VBS and VBS is held constant, so that it allows for a formation of the charge carriers. VGS is also constant, which is actually equal to more than the threshold voltage of the device, and we are assuming that you are in the threshold region and you can find the value. So, GSD is nothing but the source to drain conductance. If you take 1 by GSD, actually it will give you the source to drain resistance, right. This will give you the resistance value. Very interesting and very simple to understand. Therefore, if you want the current to be high, obviously you want that del ID should be much larger, sensitive to variations in del VDS. But as I discussed with you in the earlier classes, that you will have, if you have your current versus voltage, this is my current and this is my voltage. So, if I plot current versus voltage, and this is almost a straight line which you see, then if you are biasing a device here in these regions of operations, right, in these regions of operations, then you end up having what? You end up having that if you bias it here, then the change in the current, drain current, will be almost 0 even if you change the drain bias, right. So, the change in the current will be relatively, will be 0, almost 0, if these are absolutely straight lines which are coming, which means the current is independent of voltage, then what I will get here is that GSD will be approximately equals to 0, and therefore RSD will be approximately equals to infinity. This we have already discussed earlier, and this is one of the small signal parameter which helps you to explain the resistance of the device. Whereas, if you would have kept it somewhere here, right, or here or here, then this is almost a linear region of almost a linear region, let us assume. Then I will have a fixed value of the channel resistance available, which will depend upon 1 by GSD, right. So, you have learned 3 important parameters, one is GM, another is GMB, and another is GSD. These 3 parameters we have learned as the small signal equivalent parameters for the device. Now, if I assume this to be true, or these materials to be true, then let us see what corresponding changes we would expect to see in the device. So, if I take up this equation which is shown here, this one, we say therefore, the overall change del IDS, keeping in mind that all the 3 are now present, is del ID del VGS with del VGS here then del IDS del VBS with the del VGS here, and del IDS del VDS del VDS here, correct, which means that I have a DC bias being inserted, and over and above that I have an AC signal being inserted, which gives you a variation in drain to source, bulk to source, and gate to source. And if you add those three together, you will get del IDS. Now the problem is not the problem, but I have written here all plus, and you can see it will be plus as well. So what you will see is that if you increase the gate voltage, obviously your drain current will increase, and that is the reason the first term will be positive in nature. Similarly, if you change the value of VDS, if you increase the value of VDS, ID will never come down, it will always go up. So this is also a positive value. Similarly, look at this point, when you change the value of VBS, you just see how IDS will change, right. I leave as an exercise to you to figure it out yourself, that if I change bulk to source potential, right, it is a p type substrate, I am giving a positive bias to the bulk, I am increasing the positive bias, then what happens to my drain current, right, just like look into it. Depending on if the drain current is increasing or decreasing with bias, I will have this positive change to negative depending upon what type, but my generic equation shows me these to be all positive. So you go on adding these small signal component. To showcase that, we have drawn it from the Cividis book which we have taken, and we have therefore given the reference for the Cividis book here. Let me show you what the idea here is. Therefore you see, this is my gate, this is drain, source, and bulk. So let us start with gate. Gate will have VGS 0. This is my DC bias which I am giving to the device to be operated well above threshold, right. So VGS 0 is basically my DC source. This is my DC voltage. Del VGS is what? Del VGS is the change in the. So please understand, I am not inserting an AC signal here, but I am inserting a signal, maybe a DC signal, which is varying over and above the VGSO. So I have a VGSO fixed point, right, and then it varies like this and this, it goes up and down depending on the variation in the value of VGS, in a very low frequency mode. Similarly, we have VDSO, again positive bias with respect to source, and superimposed on that you have del VDS, we have VBSO, and we have superimposed on that del VBS. And you see interestingly that the current which is flowing is obviously in the external circuit, it flows from source to drain. So you see I have written here IDSO plus del IDS as the total current flowing through the device. So this is the total current which is flowing through the device depending on the variation here, right, and this gives you a small signal change or variation in the value. Now if I assume that the finite differences go to 0 in the limit, then automatically I get del IDS equals to GM times del VDS, GMB times del VBS, GSD times del VDS, correct, and this will give me a value of del IDS. Over and above, we also take into consideration the value of del IG and del VB to be equals to 0, which I have already discussed with you earlier. Okay. So the above these three equations which you see, the this and this, they can be represented by a small signal equivalent circuit at low frequency, and that is what is drawn on the right hand side here. We will go one by one and explain to you what these are, what these small signals and how they are derived actually. So if you see, we have 4 terminals, we have already discussed this point, we have source, we have gate, we have drain, and we have bulk, correct. We have these terminals available with us. Now let us go one by one and see how it works out. So between gate and source, this is small signal equivalent, right, low frequency. So what I am doing is I am removing the DC component away from this, right. So the DC component is not there, there is no VGSO component or VDSO or VBS component, VBSO component available. So these are all variations in the values of del VGS, del VBS, and del VDS, correct. Now if you look at del VGS, it basically tells me the variation of gate to source voltage, del VBS is a variation of bulk to source, and del VDS is drain to source. Now let us look at internal one. We have already learned this is GSD, which is 1 by GSD will be actually equals to the resistance. So, if you take 1 by GSD, it will be resistance here, right, and this resistance will be between source and drain, the transit resistance between source and drain in the intrinsic resistance. This is a controlled current source, controlled current source. Who is controlling it? The gate voltage is controlling it. For a fixed value of Gm, my gate voltage, change in the gate voltage is basically changing the gate current, and that is between these two. So, the gate current component has got two parts, one is Gm del Vds, another is Gmb del Vbs. These two components will add to the current, right, and the third component which we found out in the previous slide which we saw, which is this one is primarily responsible for forming a resistance between the two. And basically, if you are doing a small signal modeling, the resistance between the two will be 1 by GSD, which we have already defined. So, we have two components to the small signal current, one is coming from Gm times del Vgs, another is Gmb times del Vbs, and these two might be additive current in a nature. When you add it, other can be like depending on the sign of the value of your the current because of Vbs, you will either add or subtract from the gate to source voltage. And this, please understand, this network or this small signal network is valid for both N type, P type, enhancement mode, depletion mode, correct. So, this is the equivalent component between them. Please understand, as of now there is no component, there is no connectivity as such between drain and gate, right, directly, and between gate and bulk directly. So, you see this, I have broken it, there is no line here between gate and drain, yes, but there will be some capacitive component later on when we do both small signal RC equivalent model, right. Okay, we will go one by one now. Let us look at body referenced. So, now we are breaking up into body referenced models, right, where we will be using source conductance model. So, GSS will be del IS del VSB. So, it is a source current which is flowing divided by the change in the value of VSB, and therefore, you see the source current is minus of VDS. This is the question I was asking you in the previous turn, that you might have a negative terminology or a negative part coming into picture. And therefore, I can write down GSS as Gm plus Gmb plus GSD. There can be three components associated with it, which means that if you take with reference to source, then I have GB0, gate to bulk, you see gate to bulk is 0, VDB0. This is again, this one is basically source referenced or body referenced, right. So, this is your VDB0, then you have got VSB0. What I am doing, I am giving a small change in the value of VSB, source to bulk. Since I am giving a small change in the source to bulk, I would expect to see a change in the current which is happening, and this change in the current will be given by del IS del VBS or del VSB. Now, we have already defined this quantity as GSS approximately equals to this. This is with the condition that the gate to bulk and drain to bulk is always constant, they are not varying, right, and this gives you a concept of source conductance or source modeling. Now, let me come to therefore, the total modeling, so I told you that now let us come to the gate current. So, if you look at the gate current, we have assumed till now to be 0, right, that is what assumption we have taken, that the gate current should be equals to 0 because the oxide layers are very thick. If the oxide layers are very thin, you can have a direct tunneling taking place between the gate terminal and the inversion layer, and therefore, you write down that Ig equals to Ig times Ig is a function of VGS, VGB and VDB, right. So, these are the functions of these three terminals which you see. If you look at the small signal exactly like in the previous turn, my del Ig change in the gate current will be G of GS gate to source, G of GB transconducting gate to bulk, and G of GD gate to drain, multiplied by the corresponding change in the value of the VGS, VGB and VGD signals, where we define GGD as del Ig del GG. What is del Ig del VGD? Del Ig del VGD primarily tells me that how my gate current is changing when I vary my gate to drain potential, right. What is VGB, how is the gate current varying when it is gate to bulk, and how my gate current is varying when I current gate to source, right, and depending on that the gate current will be changing. Now, you will ask me Why is it why does it depend upon all these factors? The reason is that when you change the, for example, the bulk bias, the effective electric field between the gate and the inversion layer changes, right, and as a result there might be some leakage current which is happening at that particular instance of time, and that is the reason we define that to be as the gate to bulk region here, or the change the current because of that here. Let us look at the body current. The body current del IB will be given by del VGS times GBS plus into del VBS GBG times del VBG, where GBS is bulk to source conductance, GBG bulk to gate, and this is bulk to drain, and similarly the change in the voltages are shown here. And if you look at the small signal leakage current model here, you see del IG is the current which is flowing here, right. You also have a del IB current which is flowing here, right. We will do this part in the next lecture, when we will do it in detail in the next lecture. Thank you.